Okay, so now we're ready to tackle a non-homogeneous first order linear ODE, and is given by dy dt plus 4y equals 2 times the unit step function, right so. So that's called the forcing function on the right hand side. Now we have an initial condition of y of 0 equals 0, so that's called the initial rest conditions. Cool. So let's gather our Laplace transform toolbox where we have the time domain and an S domain. So given y of t, the Laplace transform is y of s. If you differentiate in the time domain, you're going to have an s multiplication in the s domain. And there's no other term because we have initial rest. Now a step function transform into 1 over s, whereas an exponentially decreasing step function transform into a s shift in the s domain. Okay, so before we go on, let's draw a roadmap so we can keep track of what we're doing. So in this blob, we're going to have the time domain, and then in this blob, we're going to have the S domain. So right now, we're right here, which is ODE, and we're going to use the Laplace transform so that we're going to make our equation simpler. Okay, you know what? Let's do it. So we're going to take Laplace transform for both sides. We're going to get s y of s plus 4y of s equals 2 over s. Okay, so once we factor out y of s on the left-hand side, we get something really cool. That's the characteristic polynomial, and that's the forcing function. So they're kind of segregated. So we're going to solve for y of s, and that's going to be 2 divided by s times s plus 4. So again, one part is forcing function, the other part is the characteristic polynomial. Cool. So that's pretty much the answer for y of s in the s domain. Now our job is to see if we can find an inverse Laplace transforms. So looking at the table, we see that we have 2 parts that we can work with. So our objective now is it'd be nice if we could decompose y of s into 2 parts. So y of s equals a over s, the forcing function portion, plus b over s plus 4, which is the characteristic polynomial portion. So how do we do that? We're going to use something called partial fractions decompositions. So that's what we're going to check out next. Right then, so we're going to cut our roadmap, paste it here so we can keep track of our progress. So our next task is going to be partial fractions decomposition, where we have y of s, and we're going to divide that into 2 equal parts. So the first thing we're going to do is multiply both sides by s times s plus 4. And what it will do is you're going to basically bring the denominator to the right hand side. So we're going to have 2 equals the right hand side times the denominator term that we just brought over. Okay, so now what we're going to do is we're going to multiply s times s plus 4 into the first term and into the second term, like so. And what always happens is you're going to have lots of cancellations. And after that, you're going to clean it up so that you're going to get a times s plus 4 plus b of s. Now we're going to regroup the right hand side so that we're going to get a plus bs plus 4a on the right hand side, where a plus b is the coefficient s and 4a is a constant term. Now on the left hand side we have a constant term, and now you might wonder, what about s on the left? Well, it's actually 0. So now we can actually compare that coefficients and these 2 coefficients, and we can solve a and b by comparing both sets of coefficients. Alright, so let's do it. So the coefficient for the s terms is going to be 0, right there, equals a plus b. Whereas the constant term, if you compare them, you're going to get 2, right there, equals 4a. So that means we already got a free answer. A must be equal to 1/2. Yes! That also means we can use these 2 equations and quickly solve for b. So b is going to be negative 1/2. Oh, that's cool. So what this means is the following. We can definitely decompose y of s into 2 equal terms. Equals s, and you bring it half down there, plus s plus 4, and you bring a negative half down there. Where again, this is related to the forcing function, whereas this is related to the characteristic polynomial. What we just done is we took y of s and we made it a new y of s, and we cleaned it up by using partial fractions. Hence, we can now use our inverse Laplace transform table to find y of t, which is the final solution of our ODE. Okay, so now this equation is the one that we're going to work on next. So we're going to cookie cut this guy out, and now we're going to actually remind ourselves of our inverse Laplace transforms by looking at our toolbox. So we have the two domains where the step function transformed into 1 over s, as opposed to the exponentially decreasing step function transformed into 1 over s plus alpha. All right, so now we're ready to rock and roll. So the time domain ODE solution is actually just the inverse Laplace transform of y of s. So y of t equals 1/2 times the inverse Laplace transform 1 over s, which is the step function. Cool. Minus 1/2 times the inverse Laplace transform of 1 over s plus 4, where alpha is 4. That means we're going to use this identity. So that means e to the negative 4t times the step function. Whereas a reminder, the blue portion is the forcing function related portion, whereas the red portion is the characteristic polynomial related portion of our solution. And as a second reminder, the characteristic polynomial is related to the homogeneous solution to our ODE. Okay, so this is the final answer. And you know what? It's actually a cool linear combination or superposition of two separate solutions. And they look like this. So let's plot the forcing function-like term first, which is 1/2 times u of t. And this is going to be pretty easy. So u of t means nothing happens prior to t equals 0. And anything happens afterwards, you're going to get a smaller step. So it kind of looks like a forcing function, sort of. Now the homogeneous-like portion, or the characteristic polynomial-related term, is going to be this guy. Okay, so if we plot that, u of t still means nothing happens prior to t equals 0. And anything afterwards, you're going to have a small exponentially decreasing envelope. Now, as a linear combination, you need to watch out for the negative sign so that you're going to make the final solution of y of t, where we're going to plot this guy right now. So now I'm going to clean it up by saying y of t is actually 1/2 times 1 minus e to the negative 4t times the step function. So you see that there's superposition, right? There's the first term, which is the kind of a half step envelope, right? And then the second term, which is the actual exponential envelope, but now inverted. What that means is the following. Instead of a regular step function, our solution y of t is actually a damped step function. Oh, that's way cool. And by the way, our y of t is stable as t approaches infinity. Okay, so we're going to cookie cut these three graphs out. And the reason is we've been talking about the characteristic polynomials a lot now. What about the associated eigenvalues in the ODE solution? So we can check that out by using the intermediate equation that we saw during our Laplace transforms derivations. So again, the right-hand side was a forcing function, and we saw the left-hand side was the characteristic polynomial. Okay, so that means our characteristic equation will be s plus 4 equals 0, and our root is going to be s equals negative 4, which is the eigenvalue of the homogeneous ODE. So that means we can immediately plot the eigenvalue plot where we have the real of s axis, and since our eigenvalue is a negative real number, s equals negative 4, that means our homogeneous solution will decay to 0 as t approaches infinity. But you know what? We have a non-homogeneous case now. So where's the evidence of this? What's right there is in the homogeneous-like solution portion, where you have the decay. And this also exists in y of t. Why? Because the decay now is inverted. Awesome.